Welcome everyone. In this video, I'm going to go over Proton NMR spectroscopy. This is my second video on NMR spectroscopy. If you haven't seen the first one on carbon-13 NMR, it's a good idea to take a look at that one first of all. There is a link in the description. Let's get started. High-resolution proton nuclear magnetic resonance spectroscopy provides additional information compared to carbon-13 NMR. Proton NMR tells us how many protons there are in each environment. Splitting patterns can also be used to find out how many protons are adjacent to each proton. Although this sounds confusing, it will make more sense as we look at a few examples. Because almost every proton has spin, the area beneath each response or signal is proportional to the number of protons in that environment. This area is calculated automatically by a computer. The ratio of the areas of each signal often appears as a number on the NMR trace and is called the integration ratio. This information is not found on a carbon-13 NMR trace because the vast majority of carbon atoms are not carbon-13. Let's look at splitting patterns next. Protons on the carbon atom or atoms next to the proton in question are said to be adjacent. Adjacent protons split the NMR signal of the proton in question. If there is one adjacent proton, the signal is split into a doublet. Two adjacent protons will split the signal into a triplet, etc. This is known as the N+1 rule. I won't go into detail here about why splitting occurs. It is much more important for A-level exams that you can recognise and interpret splitting patterns rather than explain them. In reality, there are exceptions to the N+1 rule. Knowledge of these exceptions will not be challenged in exams. On the bottom left of the screen, there is a section of a molecule. The red proton is the one that we're going to look at. Look at the carbon atom that the proton is bonded to. Then, look at the carbon atom or atoms that this carbon atom is bonded to. We'll call this an adjacent carbon atom. Count how many protons are bonded to the adjacent carbon atom. These are adjacent protons. The proton in red here has 0 adjacent protons. The squiggles, highlighted in yellow, represent atoms or groups other than hydrogen. You should note that adjacent protons can occur to the right or left of the proton that you are considering. There are examples of this later in the video. In this example, the proton in red here has one adjacent proton and will produce a doublet. The proton in red in this example has two adjacent protons and will produce a triplet. And finally, the proton in red here has 3 adjacent protons and will produce a quartet. It is possible for a signal to be split by more than 3 adjacent protons. It is often difficult to distinguish the exact splitting pattern and sometimes the term multiplet is used. If we take a look at this example, the proton in red here has 6 adjacent protons to the right, to the left and beneath. You would expect that the signal for this proton would be split into 7 peaks. When analysing a substance using NMR, the signal produced by an atom is compared to the signal produced by the same atom in a reference. Tetramethylsilane or TMS is used as a reference standard for both Proton NMR and carbon-13 NMR. TMS is used because it is inert and will not chemically alter the sample that is analysed. It is volatile and can be easily removed from the sample following testing. Other reasons might include that there are many protons and carbons in the same environment, so a strong signal is produced. Also, silicon is quite electropositive. The signal is upfield of the vast majority of those produced by the sample. Let's take a look at a few examples now. So, for the aldehyde shown below, let's label up the proton environments, suggest the expected shift range using a datasheet, suggest a splitting pattern for each signal, and give the integration ratio of the signals. I've labelled the proton environments A and B. There is one proton in environment A and there are 3 protons in environment B, so you would expect the integration ratio to be 1 to 3. Using a datasheet, we can see that the typical shift value for A would be between 9 and 10 delta/ppm. The typical shift range for environment B is between 2.1 and 2.6 delta/ppm. The carbonyl carbon here, the C double bond O, prevents splitting, so A and B both have 0 adjacent protons. The splitting pattern for A will be a singlet, the splitting pattern for B will also be a singlet. The actual proton NMR spectrum for this compound is shown on the top right of the screen. You can see that this is quite similar to my representation. I have used a free spectral database from the Institute of Advanced Industrial Science and Technology. Full details are in the description. The integration ratio showing how many protons are in each environment is not shown on these spectra. However, you would expect the integration ratio of A to B to be 1 to 3. Let's complete a similar exercise now, but for methyl butanal. There are 3 proton environments here, labelled A, B and C. You would expect the integration ratio for these signals to be 1 to 1 to 6. Using a datasheet, the signal produced by the proton in environment A you would expect to see in the range of 9 to 10 delta/ppm. Environment B should give a signal at 2.1 to 2.6 and environment C between 0.7 and 1.2. You would expect that environment A would give a singlet, environment B a septet or a multiplet, and environment C is adjacent to one proton that will give a doublet. This is how I would expect the NMR trace to look for this particular molecule. The actual proton NMR trace for this molecule is shown on the top right, and you can see that this is quite similar. However, you will notice that it is difficult to interpret the splitting patterns using a real proton NMR spectrum. Next, let's take a look at the proton NMR spectrum for butanal. There are 4 different proton environments in this molecule labelled A, B, C and D. You would expect A to show a singlet between 9 and 10 delta ppm. Environment B has 2 adjacent protons. You would expect this to give a triplet between 2.1 and 2.6 delta ppm. There are 5 adjacent protons to the proton in environment C. You would expect this to give a multiplet between 1.2 and 1.4 delta ppm. And finally, environment D has 2 adjacent protons. You would expect this signal to be a triplet between 0.7 and 1.2 delta/ppm. You might expect the proton NMR for this molecule to look like this. We can see that there are 4 different signals, one for each environment. However, the splitting patterns are getting more complicated now and might be difficult to interpret on a real proton NMR spectrum. And here is the real proton NMR spectrum for this molecule. The proton label B does not clearly show a triplet. However, the real trace does show that there are 4 different types of environments and the shift values match the typical range shown on a datasheet. Finally, let's take a look at the proton NMR spectrum for propanal. There are 3 proton environments labelled A, B and C. The table shows the expected shift range for each response as well as the splitting pattern. Once again, the real proton NMR spectrum is difficult to interpret in terms of splitting patterns. However, there are clearly 3 signals and these appear to be in the expected range. Thanks for watching. I hope you found the video useful. Please post in the comments if you have any questions or suggestions. Take care and good luck with your studies.